And if you have questions, feel free to type them in the chat, or you can unmute yourself and ask. So, Nicolas.
Yeah, thanks very much. And thanks very much for the invitation. And yes, please, so if anything is unclear, also if you have any question, please interrupt. It's also more interactive in that way, rather than just sitting here alone in the office. Yeah, so I'll speak about the long-time behavior of the 2D parabolic Anderson model. And I should really say that this is with space white noise, because I know that some people in the audience, like Alex, are interested in the parabolic Anderson model with space-time noise. So in my case, the noise does not depend on time. It is constant in time, but rough in space. And this is a joint work with Wolfgang König in Berlin from the Weierstrass Institute, and Willem van Zuijlen, who used to be a joint postdoc of Wolfgang and me, and now he's a postdoc only in Wolfgang's group. And I'll start to tell you what is the final result, and after that I'll try to motivate why we want to do that, and then in the end explain a little bit how the proof goes. So we look at, well, the parabolic Anderson model, which is just the heat equation. In this case, specifically, we look at it on R2, where we have this multiplicative noise. So it's multiplied with the potential, and the potential is a white noise in space, which does not depend on time, like I already mentioned. I will explain this later a bit more, what this is, in case some of you don't know, but somehow just imagine it's a Gaussian noise, which is independent over any two disjoint regions in space. So what the noise does here and here is independent. Yeah, and this is what I call the parabolic Anderson model. And we started with a localized initial condition. So just because it's simple to think of, I always take the Dirac delta, but that's not so important. So you could take anything that is localized and positive. And the final result that we will get to is we look at the total mass of this solution. So we integrate over the whole space. And then we look at how this behaves for large times. So we take its logarithm, and then we divide by t log t. And then we show that this converges to a deterministic constant, which is the best constant in this functional inequality here, Ladyshenskaya inequality. So this tells us the mass of this thing is growing faster than exponentially. It's growing, roughly speaking, like e to the t log t times this chi here. And the same is true if we look at the supremum over all the space, over all points. It has the same behavior on this logarithmic scale, at least. And also if we take the infimum. Well, if we take the infimum over all the space, it's not so difficult to convince yourself that this should be 0 for any positive time, because we start somehow localized here in the Dirac delta, and then this is being spread out and multiplied somehow. But if I look very far away at any positive time, it will still be 0, this infimum. Right? But so here I don't take the infimum over the whole space, but I take it over, well, regions of size roughly t. So this a here is anything less than 1. So you can take a ball of size t to the a, where a is less than 1, and then the infimum will have the same growth rate. About these two results, I will not talk. I'm just mentioning them once here now, and then the rest of the talk, I will only focus on that one. But once we understand how to do this one, it's like a 2-3 page computation to go from there to here.
So is chi positive or negative?
Positive. Yeah, so it has to be, right, from this inequality here. Both are positive quantities. So it's the best constant such that, so the best C such that this is true for all f in dimension 2. Yeah, so it's mass is generated. I hope you'll understand why mass is generated in this system. It's different than time noise, which has a tendency, because of this martingale structure, this multiplicative structure, to decrease the mass. Okay. And now so this will be basically the last slide, and now I'll start from the beginning. And first talk about deriving this thing as a scaling limit, because this also gives intuition why it should behave as it does behave. And well, if we want to derive it as a scaling limit, we could think first as of a discrete parabolic Anderson model, where we go on a lattice, put a discrete Laplacian, and then some ISO Gaussian white noise is something like IID noise, so the continuum analog of IID noise. And this is basically what we do, except, well, if you do this, then this system is closely related to a branching random walk. So rather than directly going to this discrete PDE, I go to this branching random walk, and I start with this system, because there somehow the story becomes even more transparent. So what we do is we put random walkers on ZD, which are behaving independently. There's no interaction between the walkers, and they're jumping to each neighboring site with rate 1, let's say. We superimpose on that an IID potential landscape on ZD, which is given by these eta x, which is independent of the particle dynamics. And now the guys walk through this landscape, and whenever they are at a site X, they look at what the potential does there. And for example, if like here, the site X has a positive potential value, then this means the particle has good living conditions and it can multiply. So it will branch into 2 new particles with the rate eta x, which is positive. So if eta is very big, then we have a very high branching rate and lots of particles are created. Here, a few particles are created. Once we branch, we have 2 new particles, and they do exactly the same as the old one, independently of all the others and each other. If the potential is negative, then the conditions are bad and the particle is being killed with rate minus eta x, because eta is negative, so minus eta x is positive. So if you have a very negative site, you're being killed off very quickly. And now, if we call mu the number of particles and w the conditional expectation given the potential. So this means we average over the particle dynamics. This is averaged out, but the potential, the randomness here is frozen. Then it's an exercise in a first-year course on Markov processes, some of the really elementary exercise in Markov processes to convince yourself that this will solve this PDE here, which is the discrete parabolic Anderson model, where here you see the discrete Laplacian, and here you see no multiplication with exactly this potential. And so we could imagine that if we rescale this particle system in the right way, that we could end up with a continuum parabolic Anderson model. I will explain why that is not true, but at first, if you think about it very naively, you could imagine that. Let's see why it is not true. So how will this thing behave on large scales? Well, that's relatively well understood. And there is a competition between 2 effects in the dynamics from this equation. The first one is we have a discrete Laplacian here. And so if we only look at this equation, then we have a discrete heat equation, which we can solve explicitly. It's just convolution with the discrete heat kernel. And this is smoothing, you know? So if we start this localized like that, then immediately things will become smoother and even out. So this is a smoothing effect. On the other hand, if we look at this equation, where we, like this, where we take out the Laplacian, where we only have this term and this term, then the solution is just the exponential growth in each side, right? So e to the eta t times the initial condition. And so, of course, if eta is IID, you will have one value. So if you look over a bounded region, you will have probably one value, which is the largest, and you will see a bigger exponential growth rate in this site. And so therefore, well, everything will be dominated by this site. So basically the whole mass will be concentrated in this one site with the biggest exponential growth rate. So this is roughening things up very badly. And so the question is, if you look on large scales at this system, which of these 2 effects is winning? How does the solution look like at large scales? Well, and this is understood basically since work in the 90s by Gärtner and Molchanov. And there's a nice survey book by Wolfgang König from a few years ago. And the story is the noise always wins. So the smoothing never has a chance. On large scales, the solution always forms these large peaks. And ideally, I would like to show a video, but somehow I cannot play this video on the iPad. So I draw the video instead. So let's think of this as our ZD. And let me draw a potential. Let's see, I want to have a lot, maybe not so large, peak like this here. Like this, maybe one peak here, one peak here, okay. And now we start our dynamics here. at first it's only like this. Then first is diffusing out. If we let it run for a little bit, it will just get flatter and diffuse out. And at some point it finds a region here where it can multiply the mass, where the particles have good living conditions and they start branching. So we start growing here. And at first we then have a peak forming here. But then the mass generated here is also diffusing further out because the particles keep moving. And at the same time, a little bit of mass is also moving over here. So after a while, some particles will reach in this region. And here the conditions are even better than in the previous region. So they start growing even more. So a bigger peak starts forming here, which has a bigger exponential growth rate. So somehow if you simulate it and you scale it so that this one will always, so that the highest peak will always be of unit size, then this one would start going downwards. And this one comes up. And then shortly after, well, some mass will have reached here, and here the conditions are the best. So then we would see very fast exponential growth here. And this one would go down again. And so like this, you would see these peaks forming. And then if you wait longer, you'll find a region even further away, which is even better than this one here. And then you would see even faster growth there. And in this way, at any time, there should be a finite number of regions where the mass is concentrated. Maybe some of these regions would go down, some of them would go up. And yeah, this is the picture. This story that I told you now in this precision is very difficult to prove. And I think there's only results for a few very heavy-tailed potentials, but the basic story is always that. And somehow the basic story behind that is always true. And there are various incarnations of showing that. Okay, and well, this means that if we want to rescale this, so we want to get our continuum SPDE as a scaling limit, but we cannot hope to get it from this system just by rescaling space, because if we have something which forms these high peaks and we just scale out, then we would just see some Dirac deltas basically, right? Some finite sum of Dirac deltas. And this cannot be the solution of our SPDE because the solution to the SPDE is continuous. So this cannot be the story. And well, to get something continuous, which is not so extremely spiky, we should consider a small potential. So we should give the regularization a chance by tuning down the disorder, by making the potential small. So we could take this one IID with unit variance, let's say, and multiply with this prefactor. I will comment on the exponent in a second. And then, well, we can rescale space and time parabolically so that each individual particle would converge to a Brownian motion. And then we should, of course, divide by the initial mass just so that at time 0 we have a probability measure. We could also think of a Lebesgue measure as well at time 0, but let's do a probability measure at time 0. So this is the natural scaling. And if you do that, then a formal computation where somehow just you do everything as you expect it to be, but you don't check anything rigorously, will show that if we take as initial condition n to the row particles in 0, so all the particles start at 0 and they have to be n to the row, and the row will be important, then formally, if rho is bigger than d half, this thing, this particle system, should converge to, well, the continuous parabolic Anderson model. Where this here is Gaussian space-wide noise. So now let me define it rigorously. So this is the Gaussian field whose formal covariance is the Dirac delta. And rigorously, it's a Gaussian field indexed by test functions, such that this process now has this covariance, just the L2 inner product. And this corresponds exactly to independent noise in different regions of space. So this is a formal computation, but of course, this computation cannot give you the right answer. So there's something there which doesn't make any sense because, well, you can see it here, no? So this exponent, d half minus 2, indeed is small if dimension is less than 4, but in dimension 4, it is not small, and in dimension 5, it's even big. And just from the story that the particle system forms these high peaks, well, then the result cannot be true that you converge to an SPDE if you even blow up the potential, or if you don't blow up the or if you just keep the potential of unit size. So from this point, we would only expect this to work in dimensions less than 4. And this fits nicely with the solution theory for this equation here, which also only works in dimensions less than 4. Another point is that in dimensions 2 and 3, we need renormalization in this equation. And this is also not covered in this story. So actually, to bring in this renormalization, we also have to tweak somehow the assumptions a little bit. And this we can then do. This is a result with...
Just one question. So, okay, so when D is exceeding 4, then you don't believe that there's a limit of this, or it's a trivial limit, or?
So in analogy with these results on the KPZ equation in dimension 3, I would expect that in dimension 5, if you don't put anything here, 5 and higher, then you converge to plus infinity. But if you renormalize by just multiplying with a e to the big constant times t, then this should converge to the heat equation, deterministic heat equation. But it seems difficult to prove. But yeah, so this would be what I expect in dimension 4. I don't know. This is the critical case, and so this is like 2D KPZ, which is somehow still more tricky than 3D KPZ. So I don't know what should happen there. Yeah, so we stay away from that. We go to subcriticality, so where we can handle things, where we do have a solution theory for the limit. And in this work, we focus on 1 and 2. In principle, the methods allow you to do dimension 3 is just more technical. So to avoid technicalities, I mean, it's already technical, but to avoid severe technicalities, we didn't do dimension 3. And so what do we do? Well, this is what I said before, the same scaling here. This is IID, the variance is 1. This is important though, the expectation of this, at least in dimension 2, is not 0. It is slightly negative. Sorry, so this minus here is a bit squeezed in. So it's minus n to the minus d half times Cn, and Cn in dimension 2 is approximately log n. So of course, so this is n to the minus 1 times log n is something very small. But after rescaling this, this will go away, and we'll just see this minus Cn, which will become this renormalization minus infinity in the limit. So it has a crucial effect, this small shift away from criticality. And intuitively, I think it makes sense, because in this particle dynamics, the branching and killing are not really symmetric, right? So if my randomness generates, so I throw these guys IID. On average, maybe they're 0, but certainly there will be one region where it's very big, and there will also be one region where it's very small, very negative. Well, if I bring one particle to the region where it's very big, then we'll start multiplying and create a huge amount of mass. But if I bring one particle to the region where it's very negative, well, I will lose that particle, but I will not lose more than that particle. I cannot have any long-range effects. So that's why there's a slight asymmetry, and somehow mass creation is more persistent in a way. And to correct for that, we have to do this renormalization here. Yeah. Then we start with n to the row particles in 0. And well, do this parabolic space-time rescaling, renormalize to have a probability measure at 0. And then there is an interesting effect happening depending on rho. So if rho is bigger than d half, then it converges to this parabolic Anderson model, which was the thing we were after, not to get this convergence. However, if rho is equal to d half, then we start seeing random fluctuations. So you see all the particles are independent, and the more particles I start with, somehow the more I average over the randomness coming from the particle dynamics. So if I take infinitely many particles, it's somehow clear that I would take the expectation with respect to the particle dynamics, which would be the discrete parabolic Anderson model. And then it's not so surprising that here I would see the continuous parabolic Anderson model. But if I don't take so many, namely somehow at the critical scale like this, then we remain with random fluctuations, and we get something which we call rough super Brownian motion. Namely, then here there would be an additional super Brownian noise, which would look like this formally. So square root of u times psi tilde, and psi tilde is a space-time white noise, which is independent of this space white noise. So a branching noise is generated from the random environment somehow at this critical scale. Yeah, so this is this general story. Why is the dimension important? So the basic story why in singular SPDs we need these tools for multiplying distributions. This was told in a lot of talks. Let me maybe, okay, but still to be inclusive, let me maybe explain it quickly. So the point is to solve this equation. We don't have any Ito calculus or so because the noise does not depend on time. It's just given a space, we throw it, and that's it, it's fixed. So we cannot use martingale theory to make sense of that. So basically all we have is regularity theory. And now the regularity of the white noise in dimension d is minus d half, minus epsilon, let's ignore that. And if you don't know what that means, just think of it as a dth derivative of something of regularity d half. So this would lose d, and then d half minus d would be minus d half. So that's basically what it is, up to technicalities. And then the rule is that the product of these two guys will at best be as good as the worst guy, so at best be minus d half. Then we gain two derivatives because, well, u is this operator inverted if we ignore the contribution of the initial condition applied to this product. And well, it gains two derivatives because we invert the Laplacian. So we have 2 minus d half. And now the question is whether this product here is well defined. And the product of two distributions is well defined if and only if their sum is positive. The sum of their regularities is positive. And so here we have 2 minus d half for this guy and minus d half for this guy. So the sum is 2 minus d, which is positive if and only if d is less than 2. So in dimension 2, things start to fail. And this is why in dimension 2, we need renormalization. In dimension 1, we don't need renormalization. In dimension 3, we also need renormalization. In dimension 4, somehow things really go wrong, but so the equation becomes critical. I prepared a bit too much material, so maybe it's better if I skip this. If there are questions about that, I can go back to that.
So there's one question in the chat, I think about before. So the question is, what is the worst case value for the noise component and how it occurs?
Let me see.
So Anthony,
I'm
not
so worst case regularity, or what do you mean?
Anthony, can you unmute yourself? I don't quite understand your question. Or if you can clarify in the chat.
Worst case regularity. So, well, it's so you could think, so in case you take uncorrelated, just independent noise everywhere, then the regularity is always this one here, minus d half. And this occurs, well, this is somehow due to it's coming from the scaling of the central limit theorem effectively. It's a bit complicated. I'm not sure I can perform this computation right now efficiently without losing myself a few times and so, but it's so, yeah, no, it's okay. Let me try to explain. So if we take IID guys, so we think of this as living, this IID discrete guys as living on something like this, no, 1 over NZD. And we have somehow, let's say some eta tilde. And then we want to pair somehow IID guys, which are at first of unit variance living on this grid with some test function. Then we should look at 1 over n, sum over x, eta x, and this is x in Zn. And then we have here phi of x. So this would be the duality pairing, and this would be tilde. And this would be 1 over nd. Nd. Okay. This would be the natural duality pairing of this IID guys. And if they're being centered, and now we take the expectation of this thing squared, then you see by the usual, like how you prove the weak law of large numbers, you see that there's 1 n to the 2d, and then here is some x, phi x squared. And this here is in Znd. And so now somehow you have here too many, right? So this should be only 1 over n to the d, because each volume unit now on ZND has volume n to the minus d. So if you want this to be a Riemann sum approximation of the integral of phi square, you would need n to the d here. This means that the noise, if you just put IID variables of unit size everywhere, it's too small. So you have to multiply here with n to the d half. And then we would get n to the d here, and then this would cancel, and then everything would be of the same size. And so this n to the d half, which you have to multiply the noise with, this tells you somehow on the nth on the scale of order 1 over n, you're of order n to the d half. And this is then corresponding, roughly speaking, to the regularity minus d half. So if you zoom in to spatial scales of order 1 over n, you see something of order n to the d half. Yeah, and this means so of order n to the of order 1 over n to the minus d half, and this minus d half is then the regularity. And this minus epsilon is somehow like in Kolmogorov criterion, you always lose a little bit. So this means depending on the dimension can be arbitrarily bad. Now for this equation, yeah, so in dimension 4, somehow things break, because if this thing becomes worse than -2, then we cannot hope to get any more solution theory for it, basically because then inverting this still gives us something negative, and then this means the solution wouldn't be a function anymore, and then some of things really go wrong. You could, of course, think of noise which is not uncorrelated, but maybe has some better or worse structure also, and then you could get different regularities than minus d half. Okay. Yeah, let's go towards the long time behavior. Let me try to push the chat away. Okay. Yeah, so now that we derived now this model, and I still think of it as this population model, that you have this population diffusing around in this landscape. Just our landscape now is a space-wide noise, and it finds regions where it has lots to eat and then multiplies there. It has other regions where it has nothing to eat and it's being killed off. And we want to understand how the population behaves on large scales. And so we started from discrete model, made the noise small, looked on large scales, and now see an SPD. And now the question is, does this SPD on large scales still form these peaks? Which would mean for the discrete model, at least morally, well, if we tune down the noise, but look on even longer scales, then the intermittency starts appearing again. So on the scale where we looked, we got to a continuous limit, but if we would look on even bigger scales, we would still see the intermittency. Yeah, so we want to prove this picture. And okay, so I wrote you 2 or 3, but we will do everything in dimension 2. If you develop the tools for dimension 2, then it's always typically a matter of technicalities to extend it to dimension 3. Dimension 1 is basically solved, actually. So there's a very nice work by Laure Dumas and Cyril Abbé, which is from 2018 or so, was published this year in PTRF, where they look not at this parabolic model, but at the associated Anderson Hamiltonian. So this equation here, you can write as delta TU is equal to HU with this operator. So here I'm not writing the minus infinity anymore. I don't think I will write the minus infinity from now on. Let's just keep it out of the notation. And so the solution should just be e to the TH U0, right? So the semigroup generated by this guy. So if we understand the operator very well, we will understand the solution very well. And what they look at is at the first eigenvalues of this guy. And for these eigenvalues and the corresponding eigenfunctions, they show basically everything we want. They show a very good exponential localization. They understand the shape of the eigenfunction near the maxima. They understand the shape of the potential, which, so potential is a white noise, but somehow if you modify it a little bit, or yeah, then it makes sense to talk about its shape. So it then has a deterministic shape, even though it's random, but near the maxima, it has a deterministic shape, which they understand. They understand Poisson point value statistics for the eigenvalues and basically everything. Everything you would want to know, they get. And it is based on a result of on an idea of McKean. I think it goes back to McKean. I'm not 100% sure, but this Riccati transform. So through a transformation, you can reduce the eigenvalue function for this operator to a stochastic differential equation, because in dimension 1, the white noise is just the derivative of the Brownian motion. And then you can work with the Brownian motion, which is in the background, and use stochastic analysis to tackle that. And then they have some nice monotonicity arguments which are also building on the one-dimensional notion nature to get this to work. And then it's still a lot of nice ideas and work to prove it, but based on these tools, they get it. And the point is that if we want to do now dimension 2 or 3, this does not help us because it is very one-dimensional what they do. Okay, well, people did study, however, this intermittency problem for the parabolic Anderson model also on higher dimensions. So let's see what they did. And maybe we can be inspired by that. So the first thing, this goes back to this work by Gärtner and Molchanov, that people usually do is to look at moment Lyapunov exponents, and you look at how they depend on the moment, and this will then at least heuristically tell you that there is such a story of intermittency. In our case, this does not work because, well, there are no moments. Already the first moment blows up in dimension 2 after a critical time, and in dimension 3, it is immediately, all the moments are infinite immediately. As far as I'm aware, there's only one proof of that for the value in 0 in dimension 2. There's no general proof for general x, but somehow it's clear that this would be true. It's just that nobody really made the effort to work it out, but the moments will be infinite. So we cannot do that. Another important tool is extreme value analysis for the potential. So if your potential is just a random function, you can look at, well, like in the drawing I first made, you can look at the values where the function is maximal and try to understand that. So this will be extreme value analysis for Gaussian fields. This works very well in this continuum setting, in the continuous setting, but of course for white noise, well, what does psi of x mean? It doesn't make any sense. We could mollify the white noise and it makes sense, but then, so just by convolving against a small kernel here, but of course then the extreme value statistics will depend on epsilon, and it's not clear what is the right epsilon to make this work. So my intuition is that if I look at a time scale t, then there is an epsilon t, which will go to 0 as t goes to infinity, such that basically we just have to look at the extreme value statistics for this epsilon t. But I don't know how to choose this epsilon t. There is a recent work by Lamar who looks, well, not really at that, but who has some results about epsilon t going to 0 with t going to infinity, and this might give some indication, but I'm not, I don't have any clear ideas about that, how to make that work. Our idea is how it should work, and what we're thinking about currently is to use extreme value analysis for the eigenvalues of the Anderson-Hamiltonian. So you look at the Anderson-Hamiltonian on a large box, cut it into smaller boxes, and then you compare the eigenvalues on the different boxes, eigenvalue here, 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 and so on. And well, basically the eigenvalue on the big box will be the maximum of the eigenvalues on the smaller boxes, and they will all be IID. And so you can do extreme value statistics for that. So yeah, like I said, we're thinking about that, but we don't have anything even resembling final results on that. So it's just very preliminary. So since we don't know how to do the intermittency, we do something else. And this is what I present here. So this is this global long time behavior. So rather than now proving some geometric picture, we look at just the mass of the solution. And we want to understand how this behaves as time goes to infinity. And well, there are some known results, and I want to discuss them a bit in detail because it will somehow, there's a threshold of a certain parameter appearing in these results that we then have to cross. So if the psi is a continuous function, smooth Gaussian potential, then it's known since 95 by Carmona and Molchanov that we have this asymptotic. So the logarithm of u behaves like t times root of log t times this explicit constant, which is somehow very easy, very nice to understand. Gärtner and König and Molchanov a few years later also got a second order term, but we don't, let's not worry about that here. And then not so much happened in the continuum. In the discrete, people worked on this, but in the...
So this result, is this for a centered?
Yeah, centered.
So there's no renormalization or anything like that?
No. Yeah, centered.
When you take your renormalization, can you somehow get a hint of the result that you're getting? You know, if you choose a lower value and then you figure out what happens as the smoothing goes to 0.
So in our case, in both cases it's somehow logarithmic, but I think this so in our case, with the renormalization, we will see here log t to the 1, and the renormalization is also like log n to the power 1. But I think that's a coincidence, because in dimension 3, the renormalization should be n of order n, and the power of the log should be then log t to the power 3/2, I think. It's a good question. I should think about that. Actually, I don't right now. I don't see it, but there might be something I should think about it. Yeah, I actually take a note. I do have a conjecture how to read off the growth from regularity properties of the potential, which I'll show on the next slide. But I'm not sure if it's related to the renormalization. Yeah, so Chen then in 2014 looked at distributional Gaussian fields. And I think this is the first work in that direction where he does distributional Gaussian fields. So for example, here where the correlation is such a Riesz potential, so you see alpha is positive, so this is negative. So if x is equal to y, we have 0 to the minus alpha. So it blows up as x approaches y. So this is not a function valued field, it's a distributional field with this constraint here. And he gets this exponent, 2 divided by 4 minus alpha converges to some deterministic constant, which you can write down, but it's long. He also looked in the same paper at the 1D white noise and gets the exponent 2/3. And then there's a more recent work by Chakraborty, Chen, Gao, and Tyndall, where they get the exponent. So they look at a fractional Brownian motion in 1D of first index h between 0 and 1, and they get 1 divided by 1 plus h as the exponent. It seems a bit arbitrary that I tell you all these exponents, but there's a story here, because if we look at all of them, so okay, the best exponent, the lowest one we get here on the logarithm is always 1/2. Then all of these are higher than 1/2, if you think about it a bit. And if you think about it a bit more, you also realize that they're also all less than 1. And somehow, if we make the h here very close to 0, so the regularity of this fractional Brownian motion, or derivative, so the potential is derivative of fractional Brownian motion, gets worse and worse and worse, then this here approaches more and more the 1, right? But we never get equal to 1. And if you were very attentive, then probably nobody remembers, but on the first slide I was saying that in our case we get exactly gamma equal to 1. And I claim that this is really a barrier for all the methods used in these papers, because in that case we need renormalization. And my claim is that the gamma is related to the regularity of the potential. So if the potential has regularity minus kappa, then I claim gamma is equal to 1 divided by 2 minus kappa. This does not work if kappa is negative. So if the potential actually has positive regularity, then we always get 1/2. But if the potential has negative regularity, then we get this exponent. I have no idea how to prove this, but it is true in every single example. So I believe that this is the right answer. And then you can note that gamma, just if you have this relation, gamma is less than 1 if and only if kappa is less than 1. And well, kappa equal to 1 to minus 1, this regularity is somehow the threshold where we start needing renormalization. So if we do again the power counting for the product, so if this has regularity minus kappa, then the solution should have regularity 2 minus kappa, and then the sum of the regularities is 2 minus 2 kappa, which is well posed if and only if kappa is less than 1. And another story, well, okay, let me skip this one because I'm a bit slow, and I'll get back to that anyways. So, okay, but just to summarize here, so I believe that this gamma equals to 1, which we get now is exactly because we have the threshold where we need renormalization for the first time. And if you need worse renormalization, then you'll get even higher exponents gamma here. And in principle, so the equation is solvable with regularity structure techniques whenever kappa is less than 2. So in principle, you could get any exponent here arbitrarily close to infinity. But so log t to the 1 million or so should be achievable. Right, so how do people typically prove this? The first step is they write down a Feynman-Kac representation. Well, it's a heat equation with a multiplicative noise, so you can write this as this expectation, where I should stress that now the expectation is only hitting the B, and we're freezing the Xi as conditional on Xi. So from now on, we always treat the Xi as deterministic, basically. Then in the second step, we want to go to a box. So you see the Brownian motion until time t, we only look until time t, it doesn't want to go further than actually minus root t, right? Basically, this is how far it wants to go. So you can imagine that I don't have to look at all trajectories. I can restrict to trajectories that don't get too far from the origin at the price of making a small mistake. However, you cannot do this thing with a root. You have to be more permissive. You have to take a box of order t. So here we require the Brownian motion stays in this box for all times until t, because, well, it's extremely unlikely that the Brownian motion leaves a distance t to the alpha, where alpha is now bigger than 1/2. But by allowing it to go so far, we also have much better chances of throwing a large value of these independent random variables, which form our potential. And there's a trade-off between the two. And by allowing it to go this far, somehow we achieve the optimum. So we reach big values of the Xi, and it's still relatively likely that the Brownian motion can go there. But now, if we would allow it to go even further, then the probability of going there would be so small that even the larger values of the Xi could not make up for that anymore. And why do we do this restriction to the box? Well, like this, we can relate it to the Dirichlet parabolic Anderson model. So this is the same thing. So the total mass now of this equation, except that we solve this equation on the box with Dirichlet boundary conditions on the outside of the box. 0 Dirichlet boundary conditions. And why do we want to do that? Well, because we want to do spectral theory for this operator. So the Anderson Hamiltonian on the full space might or might not have a discrete spectrum. It's not so clear. In any case, I think this is related to Anderson localization. And in any case, this proving this, that the operator on the full space has discrete spectrum, would be a very deep result and much more difficult than what we're trying to do. So somehow we definitely don't want to use that the operator has discrete spectrum on the full space. But if we go to a box, then it is trivial that it has discrete spectrum because it just follows by the spectral theorem for compact symmetric operators. And so this operator here on this box with Dirichlet boundary conditions then allows us to write the solution on the box as this spectral series here, where these are the eigenfunctions, the ENQT, and the lambda NQTs are the eigenvalues, they're decreasing, and we have a spectral gap. The spectral gap follows from an infinite dimensional version of the Perron-Frobenius theorem, basically. Same as for irreducible Markov chains. And then from this representation, you see that, well, if you have this series here for this quantity that interests you, or, well, the integral, then you just put the integral here. You have this series, and this term for n equals 1 has the fastest exponential growth, and all the other ones, well, there's a gap here, so have lower growth. So you would expect that on the level of logarithmic asymptotics, only the first term counts, so that you can isolate this one. And indeed, this you can do. So with some work, let's say, you can then show that the mass on this box is given by e to the t times the first eigenvalue. And then you have to study the asymptotics of this eigenvalue, which is now a static problem as t goes to infinity. And there are results of that type that then divided by log t to the gamma, it goes to some deterministic constant. And then if you bring everything together, so we get the total mass, divide by t log t to the gamma. This is approximately to the Dirichlet mass. The Dirichlet mass, well, this is approximately equal to the logarithm of e to the t lambda 1. but then log and e cancel, so we get this one, then the t's cancel, and so it's lambda 1 divided by log t, and this is approximately equal to the c. So going through this program gives the proof. And now we want to do this in our setting. So we want to write down the Feynman-Kac formula, and we fail immediately. So in our case, 2D white noise has regularity -1 minus epsilon, which means you cannot make sense of this random variable. So if you take an independent Brownian motion and you try to push it into the white noise and to make sense of this thing, well, it does not work. So you can try to modify the white noise, then it's well-defined and pass to the limit, but it will not converge. So this is not a well-defined random variable. And if this is not a random variable, then what is this expectation supposed to be? Right? So we're stuck. There is a work by Kanizawa and Chuk where they find a representation of this mass in terms of not the Brownian motion, but some path measure. So instead of taking expectation with respect to Brownian motion, you take expectation with respect to a certain random polymer measure. And based on that, they get this Feynman-Kac representation, but the problem is that their random polymer measure depends on the solution of the parabolic Anderson model. So we want to study the parabolic Anderson model through the Feynman-Kac representation, through the random polymer measure, but this again depends on the parabolic Anderson model, so it's circular. I tried to make this work, I couldn't do anything with this. But the main idea is the right one. So we should not try to take an expectation with respect to the Brownian motion. It should be a different path measure, but it should not be the polymer measure. It should be something in between, roughly. This is the main idea of this work that we have. So we have to change the measure so that everything makes sense, but so that we still understand the measure with respect to which we're integrating. And how to do that? So, okay, I don't have so much time, and this is now, well, let me explain this Ito trick, and then I'll skip a few technicalities. I have a lot of technical stuff prepared towards the end. So yeah, let me explain this Ito trick. Somehow this carries the main idea, and after that, there's a few technical steps to do it over and over again. So we want to make sense of this random variable where the Brownian motion goes through Xi. And so the Ito trick, which probably also many of you know, and if you don't know, then, and if you take one thing away from this course, then it should be this, from this talk, it should be this Ito trick. The idea is that we solve this equation here. And if you know about elliptic PDEs, you will probably complain that, well, we cannot always solve this equation. There are solvability conditions that the Xi has to satisfy, and the white noise will certainly not satisfy these solvability conditions. Well, let's ignore that. In reality, you have to do something like this. So 1 minus, and then you can solve it. But so to avoid technicalities, let's pretend we can solve it. And then we apply Ito's formula to the solution Z. Well, we have this martingale term here, and here we get the Ito correction. There should be 1/2 here. I also don't want to bother with all these factors of 1/2 everywhere, so I ignore that, pretend that 1/2 is equal to 1, and then this here will just be, because of this identity, the quantity that interests us. So now we bring this to the other side, we bring this to the other side, and we have this identity. And this is the Ito trick. And why is this useful? Because we gained one derivative. See, if this thing here, for example, has regularity negative minus 1 plus epsilon, then by elliptic regularity theory, this Z here will have regularity 1 plus epsilon. And here, well, this means these are continuous boundary terms. And here we take one derivative, but Z has 1 plus epsilon. So this still has regularity epsilon, so it's actually a continuous function. And of course, I can make sense of such a stochastic integral if the Brownian motion just goes through a continuous function. So that's fine, no? And so this thing, which a priori makes no sense, now is completely well defined, and we even get good probabilistic bounds on that. We can control moments and everything. That works exactly if the regularity is -1 plus epsilon. And in our case, the regularity is -1 minus epsilon. So this is again this phenomenon that we actually need renormalization. So in our case, it exactly fails. But let's still take this representation and plug it. So we wanted to control the X here with the exponential of this guy. So let's plug now this representation into here, let's say formally, or everything is modified if you want. Then we see, okay, these boundary terms. And then we see this thing here in an exponential. And as stochastic analyst, somehow this screams Gaussian, no? So you want to make this a Gaussian so that you can do a measure change. So we do that. So we complete the Gaussian exponential, add this term back in, then use this as a measure change. So this goes away. And in this way, we can write the whole expression as expectation of these boundary terms, which go here, and this term, which goes here. Except that now it's not expectation with respect to Brownian motion, but with respect to the solution of this SDE, where we have this drift, the gradient of Z. And it's a weak solution to that SDE. Okay. Well, and now let me skip a few steps. This is still not sufficient. We need to do this whole thing once more. And yeah, this I think is the representation. And after we do it once more, the thing works. So this is the same Z that we had before. Y is the solution to some other equation of the same type. W is just the sum of these two guys. X solves the equation with drift gradient of W, additive noise. And then here we have something like this, where now every term in the exponential is a continuous function. So everything is perfectly well defined. So this is the rigorous version of the Feynman-Kac formula for the 2D parabolic Anderson model. And if you have a more singular noise, you can do the same thing, except that except that you might have to take more terms than Z, Y, and then maybe there will be U and so on. And then you would start using these trees and regularity structures. And so to build like the whole, so if you have something very complicated, you might have very many trees in this expansion here. But it will always work. So for any regularity where you can solve the equation, you can find such a representation. Okay, and the point though is that the diffusion here has a drift, which is the gradient of Z. And the gradient of Z, this was the whole problem why we had to do this whole measure change argument, is not a function, it's only a distribution. So we get for our path measure a diffusion with distributional drift. Okay, but there are solution theories for that. We can use this one. So for example, Brock's diffusion is a very early example. So people have looked at diffusions with singular drift for a long time. This one here is one that is applicable to us. Basically, the idea is you reduce it to the martingale problem, which is a PDE. And then in this PDE, you can deal with distributional coefficients and you can solve it. Yeah, sorry, I have too much. Okay, so, and with this, now we can construct this process. Everything here is a continuous function and everything makes sense. So this Feynman-Kac representation is okay. Step 2, we want to do this restriction to a box. And for that, we need two ingredients, bounds on the growth of these guys, which follows from very coarse PDE estimates. You don't need much for that. And then, well, you need to understand this process. In this first story that I told you that we can restrict to minus GT because the Brownian motion doesn't want to go further than root T or so, we know what the Brownian motion wants to do. We know the heat kernel, the transition probabilities. So we need something similar for the X. And this is then the second ingredient, which I just very briefly mentioned. So we get such upper and lower. So this is the transition density of our diffusion, which has a drift, which is some distribution. So going from X at time S to Y at time T. This is this gamma, and we bound this from above and below by a standard Gaussian heat kernel with a slightly bigger, respectively, potentially much smaller variance, and times some explicit terms here, where for us it's very important because we want to look at infinite times basically. It's very important that we understand how time factors in here and how the norm of this B factors in here, because both of these terms are growing and we need to understand somehow how this is happening. Yeah, and I'm sure people who are experts in heat kernel estimates can do a better proof. My proof was I looked at Friedman's book on such heat kernel estimates, which actually deals with very different problems, but somehow the idea still works. It's just you use the fact that the heat kernel solves the Kolmogorov backward equation, and then basically you control every single term in the Picard iteration inductively. And you can write this as a series. You control every term that you sum up, and in this case, in this way, somehow you get the bounds. Very, very executive summary. Okay, and in this way, since now we can understand that the X also doesn't want to leave the region minus root t, and going outside of this region is very, very costly, we can do this restriction. So we have steps 1 and 2. Step 3, so once we have this representation, we want to do the eigenvalue as so to want to represent it by the first eigenvalue, e to the t times the first eigenvalue. And we can do this with the lower heat kernel argument, lower heat kernel bounds, and then we basically do the same arguments as in that paper by Chen. So there's not much novelty there. And in this way, we get that steps 1, 2, and 3 of this general strategy that I presented work now. So we can do this now. So we can show that the mass of the parabolic Anderson model divided by t log t behaves like lambda 1 divided by log t. So now to complete the proof, I claim that this converges to such a deterministic constant chi. Well, we have to show that this thing converges to a deterministic constant chi. So we have to understand the first eigenvalue of the Anderson Hamiltonian on a large box divided by log t. But luckily this was already done for us. So it's not like we have to prove that. So this was done in a work by Halil Çuk and Willem van Zuijlen from last year, where they prove exactly this. And so in this way, our proof is complete. So this is the last step. So this converges to this chi. Okay. Yeah, so this is the main result. We looked at this equation. That was the total mass. We showed this asymptotic. And the main things, the main contributions really were a new Feynman-Kac representation where we changed the measure. We didn't use the polymer measure and we didn't use the Brownian motion. We used something in between. This was the key tool to make it work. And then we needed heat kernel estimates for this diffusion, which appeared in between. And the last ingredient, which was not in our work, but in this previous work, were the eigenvalue asymptotics. And in this way we could make it work. So thanks.
So we can all thank Nicolas for a very nice talk. You can unmute yourself and clap, I guess. And do we have questions? You can unmute yourself or you can ask in the chat.
So this exact constant and also the t log t behavior, if you look at the discrete parabolic Anderson model in 2 dimensions, presumably you expect the t log t. Do you have a sense of how to prove that, or what the constant becomes and how it depends on the distribution?
I think it would, actually I should know this, but I would expect that, so it will not depend. So for this discrete parabolic Anderson model, let's say with Gaussian, so it will depend of course on the potential, but let's say we take Gaussian, then it will not depend on dimension. The exponent will not depend on dimension. This I'm pretty sure of. I would expect that it is something similar to this result here. To the smooth Gaussian case. But I'm not sure actually. It's yeah. Because the discrete model is so well understood, so I try to stay away from that, but maybe a bit too much because actually I should know the discrete results. Yeah, so I know more or less what's happening in the continuum. In the discrete, yeah, so naively, but it might be false, I would, expect to see something like this here, similar to that. And then if you take heavy-tailed potential or so, or what they often look at is very light-tailed, because Gaussian actually is still in the discrete world relatively heavy-tailed. So if you take like double exponential or so, that they take often because this is light-tailed and then somehow it's more difficult to understand this even. Then these exponents will definitely change. But what the exact answer is, I don't know. But there are results on that, but I just don't know exactly how it looks like.
So I have a question. In the Feynman-Kac formula you develop with this Z, where does the renormalization come in there?
Yeah, it's completely under the rug. It's yeah. So here already things are a bit fishy, right? So it should actually be, no, not here, but actually here we should look at this quantity. But of course here this thing is a linear equation. I cannot just subtract minus infinity. That makes no sense. So here I don't see it. So it doesn't appear here. It doesn't appear here. This is, yeah. So so we remain with it. So it should be minus infinity here, and then it should be minus infinity times t, let's say, on the right-hand side still. Okay, and then here's still minus infinity t. And now we start seeing it. So now we do this measure change. This is the same as before, this one here. But now here, we now have minus infinity. And this is crucial because this term here is a square of something. So I skipped this a bit in the discussion. So it's a square of a distribution, which we can make sense of. So because the z here is a Gaussian, so well, we take the gradient of that and the square of that. So it's like taking the square of a distributional Gaussian field. So this gradient z is from regularity a bit like a Gaussian free field. So it's like taking the square of a Gaussian free field. That's okay. But we have to subtract infinity here. So otherwise there's no, otherwise if we wouldn't have to, that would mean that this thing, that the thing in here basically is L2, which is of course not.
It's actually the exact same way as higher Lebesgue construction.
Yes, I think so. Yeah. So it's very, yeah, so exactly. So this transformation is actually the Heyre-Labé trick in a sense, just done on the path level. Exactly. Mm-hmm. So yeah, so in Heyre-Labé, they basically do a sort of inverse Koloff transform and start writing the expansion, start writing the first, or you can also start in more singular situations, you start writing more and more terms of the expansion that you would see for the KPZ equation into the exponential. So you use the expansion of the KPZ equation, then take the exponential of that, and this will give you the expansion of the of your multiplicative heat equation. And in a sense, this is very similar, yeah, because we have this z here, and except there's one, yeah, so there's one nonlinear effect in here. So the next one, you see here, we don't just take this operator acting on this, and then, so this would be in Heyre-Labé, they would now take the solution, the solution to this equation where this is not here. This would be the next term in Heyre-Labé. For us, it's important that we use this one here, where z is the solution to the first equation we solved. Because we want to do this Ito trick, and for this Ito trick, you always have to take the generator of the process that you're currently working with. And after we change the measure once, it's not a Brownian motion anymore. So that's why we have to take this generator. But other than that, yeah, it's more or less the same.
Any other questions?
I have a question. Can you
yes, I can hear.
Can you explain a little bit about the initial value, the choice of the initial value, and the way it sensitively changed the problem? If I understand it correctly, it's very.
So it's not important that it's a Dirac delta. It is important that, well, it's positive, okay, of course, and that it is local, so that we have something which is compactly supported. Well, it has to have finite mass, right? Because otherwise talking about the mass does not make sense if I start with infinity. I'm not sure what would happen if you take something which maybe has infinite support, but decays like a Gaussian or so at time 0 might also be okay. But somehow it makes it definitely easier to start from somewhere local and then move out from there.
So the reason I'm asking this, I'm just trying to get a feel of in terms of the physical model, how sensitive is this to the? I mean, this whole thing more sounds like a local equilibrium theory. So, like, where does it start? For instance, if you choose even something that is not spatially asymmetric, is not symmetric. Right? I mean, if you're not doing like a smooth, like a delta mass, if you're not approximating it in a smooth, in a symmetrical way, does that affect much of the problem? The local, really the micro-local character of the initial data somehow. I mean, even if I zoom in, like there could be some character that make this to be initial dependent, initial problem dependent, initial data dependent.
So non-symmetric, you mean on the level of the underlying random walk, or on the level of
No, it's the initial data in terms of approximating the delta mass.
So it's not very sensitive with respect to initial data. So you can take any initial data which so any positive measure with compact support, any finite measure with finite positive measure with compact support will give you exactly the same. So there will be no because we don't have a very fine result, no? So we only look at this logarithmic asymptotics. So we look at the
large time.
Yeah, and so we take the log, but then we divide by something big. And so if you take a mass which an initial distribution which has somehow bigger mass, for example. So this is a stupid example. I know this is not what you're asking, but if you multiply the Dirac delta with 100, it will not change anything because this 100 will come out additively here and then be killed by that term. And in the same way, basically, this is relatively insensitive with respect to the initial condition. So yeah, like I said, for any compactly supported measure, this will give the same answer. It will be the same constant here.
Yeah, okay. Yeah, so this is just like the principal eigenvalue problem exactly if you scale it correctly initially. Yeah. So second question is I'm wondering, I mean, the parabolic Anderson model from the physical sense is really a hyperbolic problem. It's really about Schrodinger equations.
Yeah.
So this is, I understand from mathematical interest, one can, but this technique, if you do the spectral decomposition, this decay problem is not the character of that, right? So
So this is of course much more difficult because by taking the parabolic problem, and this was behind all this, it's exactly that story. We only see what's happening at the top of the spectrum, or in then Schrödinger operator language would be the bottom of the spectrum. So we change the sign here somehow because it fits with our probabilistic thinking about the problem. Once you look at the Schrödinger equation, of course, you have to understand really the whole operator across the whole spectrum. And this seems much more difficult.
Okay. But also this intuition regarding this diffusion kind of a thing wouldn't apply, right? I mean, that would be also be very different natured in some sense. But is there a different interpretation in terms of Schrödinger operator instead of diffusions that you can still see the spikes? I mean, plus the the random potential, like something similar to your explanation.
Yeah, it's not so. I don't know how to say anything meaningful about that. So I don't know. So for me, here the reason why you see that is, well, the Laplacian becomes a Brownian motion or a random walk or so, then you're in the world of probability, and then you have these particles hopping around, and then you have intuition. But of course, if it's I times Laplacian, then yeah, it's not so clear. I mean, there is this whole field of Anderson localization where people do look at the whole spectrum and so on. And this is like a whole world in which I am not with which I'm not so familiar. I'm not sure if in this language then there is an interpretation of the of the Schrödinger problem that resembles this. I'm not sure.
Yeah. Well, thank you.
For the limiting constant, is there a large deviation theory for that? You know, can you pull that back to large deviations on the white noise and say something?
Yeah, that's where it's coming from. Yeah, so this here is coming from large deviation analysis. So somehow you do this argument, you cut this into sub boxes, and then you somehow rescale what's happening on the sub boxes. And in this way, you reduce the, well, yeah, by rescaling what's happening on this box to somehow a fixed size, you manage to bring it to a problem with small noise. So you have to understand somehow large deviation analysis in the small noise limit, and that is how you get this constant. I don't know the very fine details of the proof.
But do you also get a large deviation principle for the constant itself? You know, the probability that it ends up at a different constant and, you know, rate function.
So it is deterministic, right?
Well,
it's coming from a contraction principle in a large deviation principle. Basically, you do large deviations on the white noise, and then you pull this through a contraction principle to the eigenvalue. So this is basically, yeah, the large deviation principle for the first eigenvalue of random, so of an Anderson Hamiltonian with small white noise.
Okay, and that's understood in this work that you mentioned from your.
Any last questions? All right, I guess we can thank Nicolas again. And I will stop the recording.